So good morning, everyone. I should say good afternoon. So I'm Pratik Adhikary from IIT-Kanpur. I'm working with Dr. Saikat Ghosh. And so in my talk, I'll talk about a new kind of interferometer. In the first part of my talk is Polaritonr interferometer, and that in the next part, I will talk about the application of this Polaritonr interferometer in different cases. Okay, so for a conventional Mach-Zehnder interferometer, a optical field gets split in a beam splitter, acquires some phase difference, and then eventually interfere on a beam splitter. So in the output port of the beam splitter, you observe the interferences, right? So from the metrological point of view, one can ask the question that how precisely we can measure this phase difference. So the precision of the phase measurement is given by this error propagation formula, where delta I is the smallest possible intensity one can measure with the detector. So if your detector is short noise limited, then this delta I will be proportional to square root of I. So if we do this experiment, this Mach-Zehnder interferometer, if you use the initial state as coherent state, then we'll see that the sensitivity of this interferometer is given by 1 by square root of n bar, where n bar is the mean number of atoms in this coherent state. So this is called standard quantum limit. Now, if we want to go beyond that, for that actually we need quantum entanglement. So for example, if we use a known state for this interferometer, then we'll see that the sensitivity can go to 1 by n. So that is usually referred to Heisenberg limit. Okay. So this is our experimental setup, cold atom setup, and this is a rubidium cold atom trapped in a cigar-shaped moth. And this picture is taken by a webcam. And initially, we prepare this cold atom in F is equal to 2 energy level of rubidium-87 atom. And after that, we use a optical pumping beam to bring this cold atom from F is equal to 2 to F is equal to 1 energy level. And after that, we use a 2 polarizing beam to polarize this system in F is equal to 1, the middle state of F is equal to 1 manifold. So that is our state of interest. Okay. So now consider a normal 3-level system where this probe field is resonant to 1 state to 3 state. And if we see in the detector, and this data taken by an oscilloscope, that the probe pulse is Gaussian pulse. Now in presence of atom, there will be absorption, right? And if we incident a control field, which the control field is resonant from 2 to 3, so in the presence of both control and probe field, there will be a ground state coherence generated in the system along with a dark state polariton. So in this is called EIT. So that atom will trap in this dark state polariton. It will be decoupled from the probe. So probe will not see this. So as a result, we will see that transparency in the probe intensity. So you can see that there is a little bit delay of the probe beam due to change of group velocity and due to EIT. So now if we turn off the control field adiabatically, just in the middle of this probe field, the part of the probe field will get absorbed in the atomic system as a dark state polariton at the spin excitation. So after that, if after some time, if we again turn on this control field, we can convert back this spin excitation into optical field. So this is actually memory of quantum memory. You can use as a quantum memory. So this is storage and retrieve light in atomic medium. So the storage efficiency and retrieve efficiency both proportional to square root of n, where n is the number of atoms here. Okay, so now we are extending this idea in case of 4-level system, where the ground state is a F is equal to 1 manifold of this spin 1 system of rubidium atom, where we are that middle state, we are accumulating atom on the middle state. Now the control is the sigma plus control is resonant from -1 to 0. This is the F is equal to 0 state, excited state of rubidium-87 atom, and this sigma minus control is resonant from 1 to 0. And in presence of this 2 control beam and 1 probe beam, now in case of 3-level system, we have seen that there was a single polariton, but now there will be a 2 polariton, right? So we can see the interference effect between these 2 polariton depending on the phase difference between these 2 polariton. So this is a schematic diagram of this polariton interferometer, where that this is input optical field, and this input optical field generates these two different polariton, and these 2 different polariton travel in time and accord some atomic phase difference and eventually get this interference effect in the retrieve intensity. Okay, so here we plot the retrieve intensity as a function of storage time, where you can see that retrieve intensity is decreasing gradually with the increasing of storage time due to decoherence effect present in our system, various decoherence effect. So here this data is taken when we are not giving any magnetic field in the system. So, but in presence of magnetic, so this is a different region actually. When we have atomic this polariton, then when we store, we have only atomic coherence, and then after that we have this go back to the photonic state. So in presence of magnetic field, so we are giving a magnetic field along the quantization direction of our experimental setup. So as a result, there will be Zeeman shape between this spin-1 manifold, and during the storage time, there will be accumulation of dynamic phase into the system. So that dynamic phase is we are calling as phi. So when we retrieve this signal, we'll see that there is, along with this decoherence decay, there is sinusoidal oscillation. This is due to the interference between these 2 polariton. Okay, so apart from this dynamic phase, that is magnetic field, we can also give some phase difference, that optical phase difference between these 2 control field. And so in the retrieve intensity, we can observe that interference due to both optical field as well as the atomic field. So this data is, every point is actually retrieve light, and we are plotting this retrieve intensity, retrieve peak, with respect to the atomic phase, and here is the signal tone phase. That means that basically the phase difference between this atomic this control field, and we observe nice interference fringes here. Okay, so this control and probe both actually generating a 2-photon coupling here, so which we'll call as tone coupling. So because in the context of synchronization, we'll call is at tone phase. So I'll go there. Okay. So quantum synchronization we observe in our, so basically synchronization we observe in our nature in various phenomena. So for example, if we have 2 oscillator, initially 2 oscillator is oscillating in 2 different frequency. So now if we can couple these 2 oscillator with a weak coupling, then after some time we will see that they are oscillating with a single frequency, right? Depending on the initial phase difference. So basically they can oscillate in phase or out of phase, but the frequency will be same. So this is called classical synchronization. So this actually people observed many years later, earlier, that Huygens observed this. So this we can observe many phenomena, natural phenomena. So the basic criteria to synchronize a classical system with an external field or another oscillator is to have a stable limit cycle. So a stable limit cycle is a closed loop in a phase space such that any amplitude perturbation will not affect the cycle, but any phase perturbation will remain forever with the cycle. So basically limit cycle is phase insensitive. So that is the basic difference of limit cycle from this force driven oscillator, because force driven oscillator, you see, if we just perturb this force driven oscillator, the phase information will also go out. But in case of limit cycle, the limit cycle preserve that phase information. Okay, so this is classical in synchronization. Now, recently, Alexander Rule and Christoph Bruder, 2018, shows that in case of quantum system, spin half system cannot be synchronized due to lack of this limit cycle. But the next upper thing, that is the spin one system has a valid limit cycle, and we can synchronize spin one system with the external source. So here you can think of a spin one system where initially all this is well distributed, the atom is distributed over the all level of spin one system. Now, if we apply some decay beam from eighth state to this middle state, then we can accumulate all the atom in the middle state, and the corresponding density matrix. So basically, this decay beam will act as a this will prevent any atom leakage from the middle state to eighth state. So now the corresponding density matrix will have only the middle diagonal element, and if we plot this density matrix in phase space, we'll see that in the phase space we have a limit cycle. So this Q, we are plotting here this Q function. Q function is called Husimi Q function. This is basically projection of density matrix in spin coherent state basis, where the spin coherent state is defined like this, and this theta and phi are the parameter of spin coherent state. Okay, so here we can see that there is no localization of distribution along the phi axis in case of Husimi Q function, and this is actually quantum limit cycle. This is called quantum limit cycle, and that there is a function, and there is a function S function which actually quantifies the amount of synchronization taking place in the spin one system. So this function is basically integration in the phi direction, so it captures any localization in the integration in the theta direction, so it captures any localization in the phi direction. So in case of limit cycle, you see there is no localization, so that's why the S phi is 0. So S phi 0 means there is no synchronization, and any non-zero value of S phi will tell you that there is synchronization present in the spin one system. Okay. So now for this system, initial system, we are coupling this to spin state with this two tone coupling. This tone coupling I was talking about earlier. So this is in case of this spin one system. For our case, you can think of like this is two photon coupling, right? So this is coherent coupling. So now in presence of this coherent coupling, the density matrix will have the off diagonal term also, and this is very weak coupling. So that's why we are considering there is no atoms in the eighth state. So now in presence of this coupling, if we plot the same Husimi Q function in this phase space, we'll see that there is localization of Husimi Q function in this along the phi direction, depending on the phase difference between these two tone coupling. So this along this direction, so there is localization. So now in this case, the synchronization function, which is the S phi, is non-zero for this case. So then we can say that there is synchronization of the atomic system with the external source, external phase of the external source. Okay. So this is the basic idea of quantum synchronization. So now I'll show that we are actually measuring this synchronization function experimentally, and we get this phenomenon, actually synchronization phenomena. Okay. So this is our interference fringe of the Polaritonr interferometer, and we have nice interference fringes, and this fringes is due to that equal decay ratio, just gamma D and gamma G. When these two decay are equal, right? So we get nice interference fringes. Now from the visibility of the fringes, if we plot this synchronization function, which actually showing us different region where the synchronization happening for our spin one system, and if you see that along this, when the two tones, that is two control are in phase, there is non-zero value of synchronization function, so which showing that there is synchronization, the system is synchronized to the external field. But the interesting thing happens when the two tones are out of phase. You see, there is, when two tones are out of phase, the value of the synchronization function is 0. This is because the system does not have any preferred phase to log. This is called synchronization blockade. This happens due to destructive interference between these two polariton. So now the system does not have any preferred phase. He does not know that idea of the phase here. So that's why this destructive, this synchronization blockade comes. Now the scenario changes if we introduce asymmetric decay ratio. So now we are just changing the decay ratio. For asymmetric decay ratio, we see that obviously the visibility of the fringes will decreases. But when we plot the synchronization function, we observe that for all value of all the region, we have the non-zero value of synchronization function, which tells us that our system is now synchronized to the external source. Okay, so this is one of the primary result to observation of synchronization in spin-1 system. Okay, so now I will go to quantum metrology. So for quantum metrology, metrology actually deals with how precisely we can measure a phase in any interferometer. So we have this setup. This is a cartoon of the Polaritonr interferometer setup. Is in the center there is cigar-shaped mott, and this is the magnetic coil, and these are different beams. So this is actually probe beam, this is a control beam, the detector, and we observe the interference due to this two polariton, and this curve I actually explained earlier. So now for this scenario, we actually considering every point, so we actually measure the retrieve intensity. So now we have a interference fringes, we have an interferometer where we can measure the phase difference very precisely. And when we consider a single point, and we saw the retrieve intensity actually increasing non-linearly with the number of atoms here. And we do our simulation, and our simulation result actually showing similar behavior. So this is the simulation and this is the experiment. The both are really matching. And so basically we have two things. We have an interferometer where the intensity is, where we can measure the phase, and the intensity is proportional to n square. And as our detector is short noise limited, so our delta I is proportional to I, which right away gives us the sensitivity as 1 by n. So reaching this Heisenberg limit. So this is the sensitivity of magnetic field measurement we are having here is around picotesla, and this is the gain of the sensitivity with respect to the lower probe and the higher probe. Thank you.
Pratik? Question? Okay, so first question.
Yes. Yes.
You always talk about the analytical pulse.
Right?
So
this is actually experimental data.
Yeah, it means yeah. I mean that when you consider the Gaussian pulse, it is an analytical pulse.
Yes, yes.
Now, when you talk about the real signal, right, that is non-analytic, like a switch on and switch off. So can you store and retrieve the signal, non-analytical signal?
I don't know actually what you mean by non-analytical.
Means you have a soft discontinuity. Achha. Like amplitude is 1.
Okay.
When I speak, it is 1.
So actually, actually practically every pulse has a RAM time. So to generate that non-analytical pulse,
but the question is here is a very difficult question.
Yeah.
When you have this switch on and switch off is a non-analytic mode, you are having a very high frequency. Right. Then how the medium will respond to this high frequency?
That I don't know. Actually, we have not studied that. That is an interesting thing to do actually.
Right.
Thanks for the idea.
Okay. Yeah. Thank you.
Yeah. Shari.
Hello. Oh, yeah.
Yes.
So can you go to that slide where you compare the interference of your theoretical experiment?
Yeah.
So here in the in the y-axis, near the edge,
Here.
top. Yeah, there should be a maxima, right? So you have a
So basically, if you see, we're talking about, so when you are scanning the magnetic field, we're actually increasing the detuning, right? So as we increase the detuning, the due to two photon detuning, the efficiency goes down. So that's why there is gradual, yeah. So but in you are also observed that, but right. So
any more question from the audience? Okay, so there is
there
an
is-
online question from Supurna. Can you flash the question?
Is there
So you
is,
can, isn't there a rise time? In reality, is it a step function?
oh,
Isn't it a smooth analytical function in reality? In the context of the last question.
yes, there is a rise time, Suparna. And so that's why actually to create a good analytical function, it's very difficult experimentally. So our rise time is nearly 100 nanosecond in this context actually. Thanks. Yeah.
Okay. If there are no more questions, then we can go to the next talk. First, thank Pratik again for this nice talk.